December 28, 1944. 1,347 hours. 18,000 feet above Luzon Strait. Lieutenant Commander James Red Hartwell's F4U Corsair screamed through thin air at 385 knots, 440 miles per hour. Behind him, a Mitsubishi is-6M50 pursued at full throttle, its pilot desperately trying to bring his 20mm cannon to bear. What happened in the next 8 seconds would expose a fatal flaw in Japanese aircraft design that no amount of pilot skill could overcome. Hartwell threw his stick hard left. The Corsair snapped into a rolling maneuver at a speed that should have been impossible. The Zero pilot attempted to follow. His control surfaces locked solid. His aircraft continued straight while Hartwell's Corsair carved through the sky like it was moving through water. The Japanese pilot had encountered what his commanders would later call the invisible wall, a phenomenon that killed more experienced Japanese aviators than American guns ever would. The Americans had solved the problem the Japanese didn't even know existed until it was too late. They called it aileron reversal. The solution was hiding in plain sight, a small spring-loaded tab on the Corsair's wing that weighed less than 2 pounds but changed the outcome of the Pacific Air War. The crisis in Japanese fighter development began not with defeat, but with their greatest victories. Between December 1941 and June 1942, Japanese naval aviation dominated the Pacific skies. The Mitsubishi is-6M0 achieved kill ratios that seemed impossible. At Pearl Harbor, Wake Island, and the Philippines, Zeros carved through American aircraft with contemptuous ease. But those victories occurred at speeds between 180 and 280 miles per hour, the envelope where the Zero excelled. By late 1943, American fighters were regularly engaging at speeds exceeding 350 miles per hour. The fundamental physics of flight were about to betray every assumption Japanese engineers had made. The phenomenon emerged gradually, documented in American intelligence reports analyzing recovered Zero wreckage and debriefing captured pilots. At speeds above 300 knots, the Zero's ailerons, the control surfaces that enabled rolling maneuvers, began to behave unpredictably. By 350 knots, they became dangerously ineffective. Above 380 knots, they reversed their function entirely. This wasn't a design flaw in the traditional sense. It was an inevitable consequence of aerodynamic forces acting on lightweight control surfaces at high speeds. When a pilot moved the control stick to roll left, the aileron on the right wing deflected downward while the left aileron moved upward. At low speeds, this created the expected rolling motion. But at high speeds, the air pressure on the deflected aileron became enormous. The entire wing structure began to twist, not just the control surface, but the wing itself. On the Zero, with its ultra-lightweight construction optimized for maneuverability at low speeds, this wing twist could become so severe that it actually reversed the intended control input. A pilot commanding a left roll might find his aircraft rolling right, or worse, locked in place entirely. Lieutenant Saburo Sakai, Japan's third-ranking ace with 64 confirmed kills, described the phenomenon in his post-war memoir. Above 600 kilometers per hour, approximately 373 miles per hour, the Zero became a different aircraft. The controls felt like they were moving through concrete. I watched American fighters perform maneuvers at these speeds that would kill a Zero pilot who attempted them. The Japanese Navy's first technical arsenal at Yokosuka had identified the problem by mid-1943. Their solution was the A6M5 variant, which featured heavier gauge wing skinning to resist twisting. But the added weight reduced the Zero's climb rate and acceleration, the very qualities that had made it formidable. The fundamental problem remained: Japanese fighters were optimized for a style of combat that was becoming obsolete. American fighter development had taken a radically different path, driven by different tactical assumptions and, crucially, by different industrial capabilities. The chance-fought F4U Corsair, which entered service in late 1942, weighed nearly twice as much as a Zero, over 14,000 pounds fully loaded compared to the Zero's 6,500 pounds. This weight difference reflected fundamental design philosophy. Where Japanese engineers sacrificed everything for agility and range, American designers prioritized speed, firepower, and, critically, controllability across the entire performance envelope. The Corsair was designed from the outset to fight at speeds exceeding 400 miles per hour. But even the Corsair's designers encountered aileron problems during testing. At high speeds, the massive fighter's ailerons required forces exceeding 50 pounds to achieve full deflection, beyond what most pilots could physically apply in combat conditions. Test pilots at the Naval Air Test Center in Patuxent River, Maryland, reported that high-speed rolling maneuvers were prohibitively difficult and that combat effectiveness is severely compromised above 350 knots. The solution came from an unlikely source. George F. Chaplin, an aerodynamicist working for Chance Vought, had been studying a device originally developed for large transport aircraft, the servotab. The principle was elegant in its simplicity. Instead of having the pilot's control input directly move the aileron, it moved a small tab on the aileron's trailing edge. This tab, moving in the opposite direction to the desired aileron movement, created an aerodynamic force that helped push the aileron itself. But Chaplin's innovation went further. He designed a spring-loaded version, the spring tab, that provided variable assistance based on airspeed. At low speeds, where control forces were already manageable, the spring absorbed most of the tab's movement, providing minimal assistance. At high speeds, where aerodynamic forces became extreme, the spring compressed fully, allowing the tab to provide maximum assistance. The device weighed 1.8 pounds. It measured approximately 8 inches long and 3 inches wide. It would prove more decisive than aircraft cannon 3 times its weight. The spring tab system was retrofitted to F4U Corsairs beginning in February 1944, with the modification designated F4U-1D. According to Bureau of Aeronautics records, the installation required approximately 12 hours per aircraft and cost $47 in parts, roughly $820 in today's currency. What it purchased was nothing less than complete air superiority at high speeds. Test data from Patuxent River documented the transformation. An unmodified F4U-1 required 52 pounds of stick force to achieve full aileron deflection at 400 miles per hour. With spring tabs installed, that same deflection required 11 pounds, well within the capability of any pilot, even during high-G maneuvers. The roll rate improvement was dramatic. At 380 knots, an unmodified Corsair could achieve approximately 65 degrees per second of roll rate. With spring tabs, the same aircraft achieved 110 degrees per second. This meant a spring tab-equipped Corsair could complete a full 360-degree roll in 3.3 seconds at speeds where Japanese fighters couldn't roll at all. But the advantage extended beyond mere numbers. The spring tab system provided something even more valuable: predictable, linear control response across the entire speed envelope. A pilot could execute identical stick inputs at 200 miles per hour or 400 miles per hour and get proportionally similar aircraft responses. This consistency allowed pilots to develop muscle memory that worked in any combat situation. Japanese pilots had no such luxury. The Zero's control characteristics changed radically with airspeed. Maneuvers that worked perfectly at 250 miles per hour became impossible or inverted at 350 miles per hour. Every engagement required constant mental recalibration of how the aircraft would respond. The tactical implications emerged swiftly in combat. Marine Fighter Squadron VMF-214, the famous Black Sheep Squadron commanded by Major Gregory Pappy Boyington, received spring tab-equipped Corsairs in March 1944. Their combat reports from operations over Rabaul documented a revolutionary change in tactics. Previously, Corsair pilots had been instructed to avoid prolonged turning engagements with Zeros, which could outturn them at low speeds. The new guidance, issued in April 1944, read, "Maintain high speed at all times. Execute high-speed rolling maneuvers to defeat enemy attacks. The Zero cannot follow." Lieutenant Robert Duke Henning, flying with VMF-214, described his first engagement using the new tactics in his combat report dated April 17, 1944, encountered 6 Zeros at 16,000 feet. Maintained speed above 350 knots. When trailing 0 achieved firing position, executed hard rolling pull at full throttle. 0 pilot attempted to follow. Observed his aircraft enter uncontrolled roll. He recovered but lost over 4,000 feet altitude. Repeated maneuver twice more. Third time, 0 did not recover. Observed aircraft enter flat spin. No parachute observed. The Japanese response revealed their desperation. Intercepted radio communications, decoded by Fleet Radio Unit Pacific, FRUPAC, showed increasing confusion and frustration among Japanese fighter units encountering Corsairs. April 23, 1944, 1,420 hours. 0 pilot to wing commander, American fighter executing impossible maneuvers at high speed. Unable to track. Requesting guidance. April 23, 1944, 1,437 hours. Wing commander response, reduce engagement speed. Force enemy into turning fight. April 23, 1944, 1,451 hours. 0 pilot, enemy refuses to reduce speed. Cannot maintain pursuit above 600 km per hour. Controls unresponsive. The Japanese Naval Aviation HQ issued Emergency Technical Bulletin 147 on May 2, 1944, based on analysis of combat reports. The bulletin, captured after the war, acknowledged, American Corsair fighter demonstrates superior control effectiveness at speeds exceeding 550 km per hour. Pilots are instructed to avoid high-speed engagements. Force enemy to reduce speed through vertical maneuvers. But this guidance was impossible to implement. The Corsair's superior power-to-weight ratio meant it could maintain high speeds even in climbs. Attempting vertical maneuvers simply allowed Corsair pilots to gain altitude advantage while maintaining their speed buffer. The spring tab's success exposed a wider chasm in Japanese aviation technology, not just in specific components, but in the entire philosophy of aircraft development. By 1944, this gap had become unbridgeable. Japanese engineers were not ignorant of servo-tab technology. The Kawanishi N1K2J Shidenkai fighter, which entered service in late 1943, incorporated combat trim tabs, a related but less sophisticated system. These tabs could be adjusted on the ground to reduce control forces, but they provided no automatic assistance that varied with airspeed. The critical difference lay in manufacturing capability and design integration. The spring tab system required precision machining, high-quality spring steel, and careful calibration. Each tab needed to be individually adjusted to match the specific aerodynamic characteristics of its installation point. This required manufacturing precision that Japanese industry, increasingly degraded by American strategic bombing and resource shortages, could not consistently achieve. American industrial capacity, by contrast, had hit full stride. The Chance Vought factory in Stratford, Connecticut, was producing 400 Corsairs per month by mid-1944. Each aircraft received spring tabs as standard equipment, with quality control procedures ensuring consistent performance. The Brewster Aeronautical Corporation plant in Long Island and the Goodyear Aircraft Company factory in Akron, Ohio, produced additional Corsairs under license, all to the same exacting specifications. Japanese aircraft production told a different story. The Mitsubishi plant at Nagoya struggled to produce 180 Zeros per month, with quality declining steadily as experienced workers were drafted into military service and replaced with conscript labor. By late 1944, variance in aircraft performance had become so severe that pilots conducted extensive test flights before combat missions to understand their specific aircraft's quirks. Lieutenant Yasuo Kuwahara, a Zero pilot who survived the war, described the situation in his post-war account. No two Zeros flew the same. One aircraft might have heavy ailerons and light elevators. Another might be the opposite. We learned our aircraft individually, like samurai learning their specific swords. But the Americans, their aircraft were identical. A pilot could switch aircraft and notice no difference. This consistency extended to combat damage repair. When a Corsair returned with battle damage to its control systems, replacement parts were functionally identical to the originals. Japanese maintenance crews often had to custom fabricate replacement components, leading to further performance degradation. The operational impact became measurable by mid-1944. Analysis of combat reports from VMF-124, operating from Peleliu, showed that Corsair pilots achieved an average kill-to-loss ratio of 11.3 to 1 against Japanese fighters between June and September 1944. This represented a complete reversal from early war ratios, when Zeros achieved 3 to 1 or better against American fighters. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow, I've saved something extra special for you. By August 1944, the Spring Tab advantage had fundamentally transformed fighter tactics across the Pacific Fleet. What began as a technical modification evolved into a complete reimagining of air combat doctrine. Commander John "Jumping Joe" Clifton, fighter director officer aboard USS Essex, issued revised tactical guidance on August 12, 1944, that represented a complete departure from previous doctrine. The document, preserved in Naval Aviation Archives, stated, Corsair formations will maintain minimum engagement speeds of 300 knots. When bounced from above, execute high-speed barrel rolls rather than turning maneuvers. Japanese fighters cannot follow these maneuvers above 350 knots. Their control surfaces lock or reverse. This guidance required pilots to fundamentally rewire their combat instincts. Traditional fighter pilot training emphasized tight turning to get inside an opponent's turn radius. The new doctrine demanded the opposite: maintain speed, use rolling maneuvers to spoil enemy aim, and exploit the enemy's inability to follow. Fighter Squadron VF-18, the Flying Phantoms operating from USS Intrepid, became the laboratory for these new tactics. Their squadron commander, Lieutenant Commander Sam Silber, implemented intensive training focused exclusively on high-speed rolling maneuvers. His training directive from September 3, 1944, outlined the new approach: pilots will practice offensive and defensive rolling scissors at speeds above 350 knots until these maneuvers become instinctive. The enemy's weakness is our strength only if we exploit it consistently. The results were dramatic. VF-18's combat reports from operations over Formosa in October 1944 documented 47 confirmed kills against 3 losses, a ratio of nearly 16 to 1. More significantly, analysis of gun camera footage showed that 89% of kills occurred during or immediately after high-speed rolling maneuvers that Japanese pilots could not follow. Lieutenant Arnold Tex Bender described a typical engagement in his combat report dated October 12, 1944, 4 Zeros attempted to bounce our division from 5 o'clock high. Called out bandits. Maintained 380 knots indicated. Lead Zero pilot fired from 800 yards, no hits. At 400 yards, I executed hard rolling pull to port. Zero attempted to follow. Observed his aircraft snap into inverted position without pilot input. He recovered after 270-degree rotation but lost firing position. Reversed my roll, gained 6 o'clock position on same Zero. Fired 3-second burst from 200 yards. Observed strikes along fuselage and wing route. Enemy aircraft caught fire and entered spin. Pilot did not bail out. The Japanese response evolved through several phases, each revealing deeper desperation. Initial tactical bulletins instructed pilots to engage Corsairs only below 500 km per hour. When this proved impossible to enforce, guidance shifted to recommending head-on attacks where the Corsairs' rolling advantage was neutralized. But head-on attacks against the heavily armed and armored Corsair proved suicidal. The F4U-1D carried 6.50 caliber machine guns with 400 rounds per gun. The Zero carried 2 7.7 mm machine guns and 2 20 mm cannon with limited ammunition. In head-on exchanges, the Corsair's superior firepower and armored cockpit gave it overwhelming advantage. By November 1944, Japanese tactical guidance had devolved into recommendations that effectively conceded air superiority. intercepted communication from Commander Minoru Genda, one of Japan's most experienced fighter tacticians, revealed the depth of their predicament. His message to fighter squadron commanders on November 18, 1944, stated, "Corsair fighter now demonstrates complete superiority in high-speed combat. Avoid engagement above 500 km per hour. If engagement unavoidable, execute vertical maneuvers to reduce speed. Accept altitude disadvantage rather than attempt high-speed pursuit." This guidance was tactically bankrupt. Accepting altitude disadvantage against an enemy with superior speed and climb rate guaranteed defeat. But it was the only response available to pilots flying aircraft fundamentally incapable of competing in high-speed combat. The spring tab advantage extended beyond individual dogfights. It enabled entirely new tactical formations impossible for Japanese fighters to counter. The Thatch weave, developed by Commander John Thatch earlier in the war, had relied on mutual support between two plane elements. With spring tabs, Corsair pilots developed the high-speed weave, a variation that maintained the mutual support concept but at speeds 100 knots faster. In this formation, two Corsairs flew parallel courses separated by approximately 1,500 feet. When either pilot was attacked, both aircraft would execute simultaneous rolling turns toward each other at full throttle. The attacker, attempting to follow, would find himself in a scissors maneuver against two opponents who could outroll him at speeds where his own controls barely functioned. Lieutenant Commander Roger Hedrick, commanding VF-84 Wolfgang Squadron, described the effectiveness of this tactic in his after-action report from the Battle of Leyte Gulf, October 25, 1944, engaged 8 Zeros attempting to reach our task force. Maintain high-speed weave at 380 knots. Zeros made repeated attacks but could not maintain firing position during our rolling maneuvers. Destroyed 4 enemy aircraft. Lost no friendlies. Enemy pilots appeared increasingly frustrated, attempting tighter maneuvers that resulted in loss of control. Observed 2 Zeros enter uncontrolled spins without taking fire. The psychological impact on Japanese pilots became evident through prisoner interrogations conducted by Allied Translator and Interpreter Section, ATIS. Flight Petty Officer Fujita Iozo, shot down over Leyte and captured on October 29, 1944, provided detailed testimony about the Corsair's seemingly impossible maneuverability. "The American fighter could dance in the sky at speeds that would kill our pilots," Fujita testified. "We were taught that our Zero was superior in maneuverability. This was true at low speeds. But the Americans refused to fight at low speeds. They fought at speeds where our aircraft became uncontrollable. It was like fighting a tiger while trapped in quicksand. Every movement we made only made our situation worse." The spring tab advantage manifested most cruelly not in dramatic dogfights but in the steady attrition of Japan's dwindling pilot pool. By December 1944, Japanese naval aviation had entered a death spiral from which it would never recover. The mathematics were brutal and inexorable. Japan's training pipeline could produce approximately 200 new fighter pilots per month, a figure that had already declined from 400 per month in 1943 due to fuel shortages and the diversion of experienced instructors to combat units. Combat losses averaged 180 pilots per month between October and December 1944, but these raw numbers masked the catastrophic reality: the quality of lost pilots. Japan's pilot training program, once the world's most rigorous, had collapsed under pressure. Pre-war naval aviators required 700 flight hours before assignment to combat units. By late 1944, replacement pilots arrived at squadrons with as few as 100 flight hours, barely enough to master basic flight operations, much less combat tactics. These inexperienced pilots faced American opponents with extensive training, superior aircraft, and tactical doctrines specifically designed to exploit Japanese weaknesses. The result was predictable and horrifying. Combat reports from Marine Air Group 31, operating from Peleliu during December 1944, documented engagements that barely qualified as combat. Captain Donald Aldrich's report from December 8, 1944, described an encounter that typified the period: intercepted formation of 6 Zeros at 14,000 feet. Engaged at 370 knots. Enemy pilots attempted to turn into attack. 3 aircraft immediately entered spins, suggesting pilot-induced stalls from excessive control input. Destroyed 2 remaining controllable aircraft. 6-0 fled at low altitude. Pursued and destroyed. Engagement duration, 4 minutes. No friendly damage. The psychological toll on surviving Japanese pilots became a factor in operational planning. Commander Masatake Okumiya, staff officer for the 201st Air Group, documented the morale collapse in his post-war memoir. Our pilots knew they were flying inferior aircraft against superior opponents. The Corsairs' ability to maneuver at high speeds seemed like magic to pilots whose aircraft became uncontrollable at those speeds. Many pilots requested assignment to kamikaze units rather than continue conventional combat operations. Death in a suicide attack at least offered purpose. Death in unequal combat offered only futility. This last observation revealed the most tragic consequence of the technological gap. The kamikaze strategy, which emerged in October 1944, was not merely a desperate tactical innovation. It was a rational response to Japanese aviation's complete inability to compete in conventional air combat. When a Zero pilot attempting to dogfight a Corsair had perhaps a 5% chance of survival and a 1% chance of scoring a kill, the mathematics of sacrifice changed. A kamikaze attack, if it reached the target, offered 100% certainty of damaging the enemy, even if it also meant 100% certainty of death for the pilot. The spring tab's role in driving this calculus was direct and measurable. Analysis of Japanese naval aviation records captured after the war showed that between October 1944 and March 1945, conventional fighter operations achieved a kill-to-loss ratio of approximately 0.12 to 1 against American carrier aircraft. This meant Japanese pilots were being killed at a rate 8 times faster than they could kill opponents. Kamikaze operations, by contrast, achieved hit rates between 14% and 18% depending on defensive countermeasures. While still resulting in the pilot's death, these attacks at least guaranteed some damage to American forces. The decision to embrace kamikaze tactics was horrifying, but from a purely operational perspective, it was less wasteful than conventional combat. Vice Admiral Takajiro Onishi, who organized the first kamikaze units, explicitly referenced the technological disparity in his orders establishing the Special Attack Corps on October 19, 1944. Our conventional fighter operations cannot achieve decisive results against enemy forces equipped with superior aircraft. The only path remaining is to maximize the value of each pilot's sacrifice through direct attack. The spring tab advantage also affected Japanese defensive operations in ways that compounded their losses. American carrier task forces conducting strikes against Japanese-held territories did so with near impunity. Corsair pilots, confident in their aircraft's high-speed superiority, provided fighter cover that Japanese interceptors could not penetrate. Strike reports from Task Force 38's operations against Luzon in November 1944 documented this dominance. On November 14, 1944, during strikes against Manila Bay shipping, 48 Corsairs provided air cover for American bombers. Japanese forces committed 73 fighters to intercept the raid. The results: 31 Japanese fighters destroyed, 7 probables, 0 American fighter losses. The pattern repeated across every major operation. Japanese commanders faced impossible choices: commit fighters to defend against American strikes and watch them be systematically destroyed, or preserve fighters by not engaging and allow American bombers free rein. Either choice led to defeat. Fuel shortages exacerbated the crisis. By January 1945, Japanese fighter units received barely enough fuel for combat operations, with none available for training flights. New pilots arrived at squadrons having never practiced high-speed maneuvers because training commands lacked fuel for advanced instruction. These undertrained pilots, flying inferior aircraft, faced opponents who had not only technological advantages but hundreds of hours of practice exploiting those advantages. The outcome was foreordained. Japan's aviation industry recognized the crisis. their response revealed both technical sophistication and the insurmountable resource constraints that doomed all their efforts. The Kawanishi N1K2J Shidenkai, entering service in January 1945, represented Japan's most sophisticated attempt to match American fighter capabilities. Engineers at the Kawanishi facility in Himeji had studied captured intelligence about the Corsair's control system advantages and attempted to develop comparable solutions. The Shidenkai incorporated several innovations: laminar flow wing designed to reduce drag at high speeds, automatic combat flaps that extended partially during high-G maneuvers to increase lift, and most significantly, revised aileron design with internal mass balancing to reduce control forces at high speeds. These modifications showed technical competence. The Shidenkai achieved better high-speed handling than any previous Japanese fighter. Test pilots at Apama Airfield reported that the aircraft remained controllable at speeds up to 650 km per hour, approximately 404 miles per hour. But remaining controllable was not the same as matching Corsair performance. The Shidenkai still required significantly higher stick forces at high speeds than a spring tab-equipped Corsair, and its roll rate at 400 miles per hour remained substantially inferior. More critically, the aircraft arrived far too late and in far too small numbers to affect the war's outcome. Production figures told the story of Japanese industry's collapse. Kawanishi planned to produce 400 Shidenkai fighters per month by March 1945. Actual production never exceeded 98 aircraft in any single month. The reasons were systemic and unsolvable. American B-29 strategic bombing had begun targeting Japanese aircraft production facilities in November 1944. The Kawanishi plant at Himeji suffered 3 major raids between December 1944 and February 1945, each disrupting production for weeks. More insidiously, raids on aluminum refineries and steel mills choked off raw material supplies. By March 1945, Japanese aircraft manufacturers faced aluminum shortages so severe that engineering teams were designing airframes using wood and fabric for non-critical components. The Shidenkai, which required precision-machined aluminum components for its advanced control systems, became impossible to produce in meaningful numbers. Even those aircraft that reached operational units suffered from quality control issues that would have been unthinkable 2 years earlier. Lieutenant Naoshi Kano, one of Japan's highest-scoring aces, described receiving a new Shidenkai in February 1945. The aircraft looked magnificent on the ground. In flight, I discovered the ailerons were misaligned by nearly 2 degrees. The canopy would not seal properly. The radio worked intermittently. These were not combat damage repairs but brand new production aircraft. Our factories were dying. Japan's last attempt to develop a technological counter to American air superiority was the Mitsubishi J2M Raiden and Kawasaki Ki-100. Both aircraft showed promise in testing, with improved high-speed handling and competitive performance. But production numbers remained microscopic. Fewer than 500 J2M aircraft were completed before war's end, and the Ki-100 entered service only in March 1945. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. The spring tab's dominance reached its apex during the Okinawa campaign, where the technological disparity between American and Japanese fighters became so extreme that engagements barely qualified as combat. Between April and June 1945, the aerial battle over Okinawa exposed the complete collapse of Japanese fighter effectiveness. Marine Air Group 33, operating from Kadena Airfield after its capture on April 1, 1945, deployed 124 Corsairs equipped with the latest spring tab configurations. These aircraft faced wave after wave of Japanese attacks, both conventional fighters and kamikaze raids, launched from airfields on Kyushu, 350 miles to the north. The combat mathematics were brutally one-sided. MAG-33's official records documented 512 confirmed aerial victories between April 6 and June 22, 1945, against 14 Corsair losses to all causes, including anti-aircraft fire and operational accidents. Only 3 losses were attributed to Japanese fighters in air-to-air combat, a kill ratio exceeding 170-1. These numbers reflected not just pilot skill but the fundamental impossibility of Japanese fighters competing at the speeds where combat now occurred. Captain Kenneth Roycer, flying with VMF 323 Death Rattlers, described typical engagements in his combat diary, April 12, 1945. CAP mission over radar picket destroyers. Intercepted 12 bandits at 18,000 feet. Engaged at 390 knots. Enemy fighters attempted to turn into our formation. Watched multiple aircraft snap into spins when pilots applied excessive control inputs trying to match our maneuvers. Destroyed 3. Observed 4 more crash attempting to recover from self-induced spins. No friendly damage. Engagement time, 6 minutes. The Japanese Fifth Air Fleet, responsible for defending Okinawa and conducting attacks against the American invasion force, lost 1,465 aircraft between April and June 1945 according to post-war Japanese records. Of these, approximately 900 were destroyed in air-to-air combat, mostly by Corsairs exploiting high-speed advantages that Japanese pilots could not counter. Intercepted Japanese radio communications revealed desperation bordering on panic. On April 16, 1945, a transmission from a Japanese flight leader to his base commander was decoded by FRUPAC, enemy fighters engaging at speeds our aircraft cannot sustain. Controls unresponsive. Cannot maintain formation. Cannot execute evasive maneuvers. Request permission to withdraw. The response came minutes later, withdrawal not authorized. Press attack at all costs. This exchange captured the tragedy of the final months. Japanese commanders knew their pilots were flying to certain death in aircraft technologically incapable of competing, yet the strategic situation offered no alternatives. Every pilot lost was irreplaceable. Every mission flown accelerated the final collapse. The kamikaze strategy, which had emerged partly in response to conventional fighter inadequacy, now consumed the remnants of Japanese naval aviation. Of the 1,465 aircraft lost at Okinawa, approximately 800 were expended in kamikaze attacks. The remaining 665 were destroyed in conventional combat operations that achieved virtually nothing. Vice Admiral Mato Magaki, commanding the Fifth Air Fleet, recorded in his diary on May 4, 1945, "Our fighter pilots face an impossible task. The enemy's Corsair can maneuver at speeds where our aircraft become uncontrollable. Sending pilots against such odds is murder, not combat. Yet we have no choice. The battle demands sacrifice, even when sacrifice achieves nothing." American pilots, witnessing the one-sided slaughter, experienced complex emotions. Lieutenant Robert Wade, flying with VMF 224, wrote in a letter home dated May 18, 1945, "It's not really fighting anymore. We have every advantage, speed, firepower, maneuverability at the speeds we fight. The Japanese pilots are brave beyond belief, but bravery can't overcome physics. They're flying aircraft that belong in museums, not combat. I've stopped counting my kills. It feels like murder." The spring tab advantage extended beyond direct combat. It enabled Corsairs to maintain continuous combat air patrol over the invasion fleet with impunity. Japanese strike aircraft attempting to reach American ships had to penetrate walls of Corsairs that could pursue them at any speed, altitude, or attitude. The few aircraft that reached the fleet had usually lost their fighter escorts, making them vulnerable to ship-based anti-aircraft fire. By June 1945, Japanese fighter resistance over Okinawa had effectively ceased. The Fifth Air Fleet had been destroyed as an effective fighting force. Surviving aircraft were hoarded on Kyushu airfields for the expected invasion of the home islands, an invasion that would never come. The final accounting was stark. American naval aviation had achieved complete air superiority through technological advantage so overwhelming that pilot skill became almost irrelevant. A mediocre American pilot in a Corsair could defeat an ace in a Zero simply by maintaining high speed and using maneuvers the Zero physically could not follow. The spring tab, a device weighing less than 2 pounds and costing $47 to install, had helped destroy an entire air force. Behind the statistics and tactical reports lay thousands of individual tragedies: Japanese pilots sent to die in aircraft their commanders knew were obsolete, and American pilots forced to kill opponents who had no realistic chance of survival. The psychological toll on Japanese aviators manifested in ways that contradicted every Western assumption about Japanese military culture. Post-war interrogations of surviving pilots, conducted by the United States Strategic Bombing Survey, revealed widespread despair and resentment among Japanese fighter pilots by mid-1945. Flight Petty Officer Yasuo Kuwahara, shot down over Okinawa on May 11, 1945, and rescued by American submarine, provided testimony that shattered myths about Japanese warrior spirit. "We knew we could not win. We knew our aircraft were inferior. Every briefing was a death sentence." Pilots volunteered for kamikaze missions not from patriotism but from logic. At least in a suicide attack, your death might accomplish something. In conventional combat, you simply died pointlessly. This sentiment appeared repeatedly in captured documents. A diary recovered from Flight Petty Officer Toshio Hashimoto, killed over Okinawa on April 29, 1945, contained entries revealing profound disillusionment. April 27, 1945. "Another mission tomorrow. They tell us to have courage, to trust in our training. But no amount of courage overcomes the enemy's technological superiority. Our Zero fighters cannot maneuver at speeds where combat occurs. We are samurai fighting with bamboo swords against men with rifles. Honor demands we try. Logic says we will die. Both are true." American pilots carried their own psychological burdens. The one-sided nature of combat created moral discomfort that many struggled to articulate. Captain Jefferson DeBlanc, a Medal of Honor recipient flying Corsairs at Okinawa, described this in post-war interviews. "You'd see a Zero trying to turn with you at high speed. The pilot would pull too hard. The aircraft would snap into a spin. You'd watch it fall, knowing the pilot was desperately fighting controls that wouldn't respond. Sometimes they'd recover at low altitude, only to stall again. You'd follow them down, waiting. It wasn't combat. It was execution. You did it because it was your job, but it hollowed you out inside." Navy psychiatrist Lieutenant Commander Robert Grinker, stationed aboard USS Bennington, documented increased psychological casualties among Corsair pilots despite their overwhelming tactical success. His medical report from June 1945 noted, "Fighter pilots report symptoms of combat fatigue despite low physical danger. Many express guilt over the one-sided nature of engagements. The lack of genuine combat challenge combined with the necessity of killing essentially helpless opponents creates psychological stress that traditional combat does not." Several pilots have requested transfer to other duties. The spring tab's role in this psychological dynamic was direct. It had transformed air combat from a contest of skill into a technological execution. American pilots knew their victory was predetermined by engineering advantages their opponents could not match. This knowledge provided no comfort. Japanese families received notifications of deaths that official communiques described as heroic sacrifices. The reality, documented in war diaries and letters that survived, was bleaker. Pilots died not in glorious combat but in uncontrollable spins, unable to follow enemy maneuvers, or in desperate kamikaze attacks chosen because conventional combat offered no hope. By war's end, Japan had lost approximately 10,500 naval aviators in combat. The majority died in the war's final year, when the technological gap had become unbridgeable. How many died specifically because their aircraft could not maneuver at high speeds remains unknowable, but combat reports and loss analyses suggest thousands perished attempting maneuvers their aircraft physically could not execute. The spring tab saved thousands of American lives by making combat so one-sided that Japanese resistance became futile. This was its purpose and its achievement. That this salvation came at the cost of making air combat into mechanized slaughter rather than a contest of warriors troubled those who experienced it, even as they recognized its necessity. The device that weighed 1.8 pounds had altered not just the mechanics of flight but the moral calculus of aerial warfare. The spring tab's influence extended far beyond World War II, shaping aviation development and tactical doctrine for decades. Its success demonstrated principles that would define the jet age and modern air combat. The fundamental lesson was unambiguous: in high-speed flight, control authority determines survivability. This principle drove American aircraft development through the Cold War. The F-86 Sabre, which dominated MiG-15s over Korea using similar high-speed rolling tactics, incorporated hydraulically boosted controls that provided the same advantage spring tabs had given Corsairs. The F-4 Phantom, F-14 Tomcat, and F-15 Eagle all featured increasingly sophisticated control augmentation systems descended from the same basic concept, ensuring pilots could maneuver at maximum aircraft performance regardless of aerodynamic forces. Soviet aviation designers, having studied captured German and Japanese aircraft analysis, reached parallel conclusions. The MiG-15's control difficulties at high speeds, the same aileron reversal problems that plagued the Zero, were addressed in subsequent designs through powered controls and later fly-by-wire systems. The technological arms race in fighter aviation became fundamentally a race to maintain control authority across expanding flight envelopes. The tactical revolution proved equally enduring. Modern fighter doctrine still emphasizes energy management and using speed to dictate engagement terms, principles developed by Corsair pilots exploiting spring tab advantages. The concepts of boom and zoom tactics and maintaining speed to preserve maneuverability options trace directly to lessons learned over the Pacific in 1944 to 1945. The spring tab itself remained in use on various aircraft into the 1960s, even as hydraulic and eventually fly-by-wire systems replaced mechanical controls. The Grumman F-8F Bearcat, designed as the ultimate piston engine fighter, incorporated refined spring tab systems. The Douglas O-1 Skyraider, which served through the Vietnam War, used spring tabs for its massive control surfaces. The principle remained valid: provide control assistance that increases with airspeed, maintaining consistent pilot control across all flight conditions. Military historians recognize the spring tab as representative of American industrial philosophy in World War II, solving problems through engineering innovation backed by manufacturing capacity. Japanese forces encountered this pattern repeatedly: American radar that negated night cover, proximity fuses that made anti-aircraft fire devastatingly effective, and yes, spring tabs that negated Japanese fighter maneuverability advantages. The personal stories of those involved provide the human dimension to technological history. George Chaplin, who designed the spring tab system, received the Navy Distinguished Public Service Award in 1946. He continued working in aerospace engineering until his death in 1972, contributing to early supersonic aircraft development. Chance-fought test pilots who proved spring tab effectiveness received recognition in aviation circles, though their contributions remained largely unknown to the public. Japanese aviation engineers who struggled to counter American advantages survived to rebuild their nation's aviation industry. Many contributed to post-war commercial aviation development, bringing hard-won understanding of high-speed aerodynamics to civilian aircraft design. The lessons learned in defeat informed Japan's emergence as a major aerospace manufacturing nation by the 1970s. American pilots who flew spring tab-equipped Corsairs carried complex memories. They had experienced overwhelming tactical advantage, achieving kill ratios that made combat almost safe. Yet many struggled with what that advantage meant: the knowledge that their survival came not from superior skill but from superior tools fighting opponents who had no realistic chance. Veterans' reunions in later decades often featured discussions of this moral ambiguity, the discomfort of one-sided victory. The final accounting remains sobering. The spring tab, combined with other American technological advantages, helped achieve victory at reduced American cost. This was its purpose. That it also made combat into technological execution rather than a test of warriors troubled those involved, but did not change the fundamental calculus. In modern warfare, technological superiority determines outcomes regardless of individual courage or skill. Today, aviation museums display Corsairs and Zeros side by side. visitors admire the Zero's elegant simplicity and the Corsair's brutal power. Few notice the small tabs on the Corsair's ailerons. Fewer still understand that those modest devices, weighing less than 4 pounds total, represented a decisive advantage that helped destroy an air force and shorten a war. The spring tab's legacy is written not in dramatic monuments but in a subtle recognition that in technological warfare, small innovations at the right moment can tip the balance between victory and defeat, survival and death. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.